Welcome to Sleepy Parallax. Long before Einstein reshaped our understanding of gravity, before anyone had conceived of spacetime as something that could bend and warp, there was a country rector in England who looked up at the stars and wondered about darkness. His name was John Michell, and in the year 1783, he proposed something so radical, so far ahead of its time, that it would be forgotten and then independently rediscovered more than a century later. Michell was not your typical 18th-century clergyman. Described by contemporaries as a short man of black complexion and considerable girth, he possessed one of the most brilliant minds of his era. He held positions at Cambridge University, teaching Hebrew, Greek, mathematics, and geology. His interests sprawled across the landscape of natural philosophy. He studied earthquakes after the devastating Lisbon quake of 1755, essentially founding the field of seismology. He investigated magnetism, discovering that magnetic force decreases with the square of distance. He even designed an apparatus to measure the mass of the Earth itself, though he would die before using it. That device would later be employed by his friend Henry Cavendish in the famous experiment that bears Cavendish's name. But perhaps Michell's most remarkable contribution came from a simple thought experiment. He was interested in determining the mass of stars by measuring their light. In Michell's time, light was thought to be composed of tiny particles, following Newton's corpuscular theory. Michell reasoned that if light consisted of material particles, then those particles would be slowed down by a star's gravitational pull as they escaped its surface, much like a ball thrown upward from Earth eventually slows and falls back down. He performed calculations. He considered what would happen if a star were sufficiently massive and dense. The escape velocity, the speed needed for anything to break free from the star's gravitational embrace, would increase with the star's mass. And then Michell made a leap. What if a star existed whose escape velocity exceeded the speed of light? Nothing could escape such an object. Not particles, not light itself. The star would be invisible, a dark body lurking in space, detectable only through its gravitational effects on nearby objects. On November 27, 1783, Michell presented his ideas in a letter to Henry Cavendish, which was subsequently published by the Royal Society. In it, he described what we would now recognize as a black hole. He called them dark stars. He even suggested methods for detecting them, proposing that one might observe a visible star orbiting an invisible companion, with the orbit revealing the presence and mass of the unseen object. Michell understood that while these dark stars would be invisible to direct observation, they would still exert gravitational influence. Their presence could be inferred, their properties calculated. The scientific community largely ignored this brilliant insight. Within a few years, new theories about light emerged. The wave theory of light, championed by scientists like Thomas Young and later confirmed through various experiments, suggested that light was not made of particles but rather propagated as waves through a mysterious medium called the luminiferous ether. Waves, unlike particles, would not be affected by gravity in the way Michell proposed. His dark stars seemed to rest on faulty assumptions, and the concept faded into obscurity. Across the English Channel, the French mathematician and astronomer Pierre-Simon Laplace independently arrived at similar conclusions. Around 1796, in his book Exposition du Système du Monde, Laplace also discussed the possibility of massive stars whose gravity would prevent light from escaping. He too worked within the framework of Newton's corpuscular theory of light. Like Michell's work, Laplace's ideas were largely forgotten when the wave theory of light gained prominence. For more than a century, the concept of dark stars remained dormant, a curious historical footnote in outdated physics textbooks. Scientists moved on. The 19th century brought electromagnetic theory, thermodynamics, and the first hints of quantum mechanics. The universe, it seemed, was becoming better understood, more predictable. Little did anyone know that the 20th century would shatter that comfortable certainty and resurrect Michel's dark stars in a form more bizarre than anyone had imagined. What's fascinating about Michel's prediction is not merely that he arrived at the concept of an invisible star, but that he did so through pure reasoning, mathematical calculation, and physical intuition. He had no experimental evidence, no observations to guide him. He simply followed the logic of Newton's laws to their natural conclusion. In doing so, he became the first person to predict one of the universe's most extreme phenomena, more than 2 centuries before we would capture actual images of black holes lurking at the hearts of galaxies. Michel died in 1793, having lived a quiet life in the parish of Thornhill, near Leeds. He welcomed scientific luminaries to his home including Benjamin Franklin, Joseph Priestley, and Henry Cavendish, but he never sought fame for his discoveries. Many of his insights were credited to others. His work on magnetism was largely attributed to Charles Augustin de Coulomb. His earthquake research went unrecognized for decades. And his dark stars, the most visionary of all his ideas, simply disappeared into the archives of the Royal Society, waiting patiently for the world to catch up. By the early 20th century, physics stood on the edge of transformation. Classical mechanics, which had served so well for 2 centuries, was beginning to show cracks. Strange experimental results refused to fit into neat Newtonian boxes. Light behaved in ways that defied simple explanation. Matter itself seemed to operate on principles that were subtle, uncertain, and profoundly weird at the smallest scales. Into this ferment stepped a young patent clerk in Switzerland. His name was Albert Einstein, and he was about to change everything. In 1905, Albert Einstein published his special theory of relativity, fundamentally altering our understanding of space and time. He showed that they were not separate, absolute entities but rather interwoven into a four-dimensional fabric called spacetime. He demonstrated that the speed of light was constant for all observers, regardless of their motion, and that nothing could travel faster than light. These ideas alone would have secured Einstein's place in history. But Einstein wasn't finished. Special relativity dealt only with objects moving at constant velocities. It couldn't handle acceleration, and it didn't include gravity. Einstein knew this was incomplete. For the next 10 years, he grappled with the problem of incorporating gravity into his relativistic framework. The challenge consumed him. He wrestled with complex mathematics, explored geometries he barely understood, and experienced moments of elation followed by crushing disappointment when his equations refused to work. Finally, in November 1915, Einstein presented his general theory of relativity to the Prussian Academy of Sciences in Berlin. The theory was revolutionary. Einstein proposed that gravity was not a force in the Newtonian sense but rather the curvature of spacetime itself. Massive objects like stars and planets don't pull on each other through some mysterious action at a distance. Instead, they warp the fabric of spacetime around them, and other objects move along the curved paths created by this warping. A planet orbiting a star isn't being pulled by an invisible string, it's following the natural geodesic, the straightest possible path, through curved spacetime. Imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a depression, a curve in the sheet. Now roll a marble past the bowling ball. The marble doesn't travel in a straight line, it curves around the depression, perhaps even spiraling inward if its speed and angle are right. This is a rough analogy for how gravity works in general relativity. The bowling ball represents a massive object like a star, the rubber sheet represents spacetime, and the marble represents a smaller object moving through the warped spacetime. Einstein's field equations, the mathematical heart of general relativity, describe precisely how matter and energy curve spacetime. They're notoriously complex, a set of 10 interrelated differential equations that relate the curvature of spacetime to the distribution of matter and energy within it. Finding solutions to these equations, even for relatively simple scenarios, is extraordinarily difficult. Which makes what happened next all the more remarkable. On the Eastern Front of World War I, amidst the mud and horror of trench warfare, a German astrophysicist named Karl Schwarzschild learned about Einstein's new theory. Schwarzschild was no ordinary soldier. Before the war, he had been director of the prestigious Astrophysical Observatory at Potsdam, one of the leading positions in German science. Despite being over 40 years old, he had volunteered for military service in 1914, caught up in the wave of patriotic fervor sweeping Europe. He served on both the Western and Eastern fronts, applying his mathematical skills to calculate artillery trajectories. In early 1916, while stationed in Russia, Schwarzschild received copies of Einstein's papers on general relativity. The war had not dulled his scientific mind. Reading Einstein's work, Schwarzschild recognized both its brilliance and its complexity. Most physicists assumed that solving Einstein's field equations would be an impossible task, something that could only be approximated under very special circumstances. Schwarzschild decided to try anyway. Working by candlelight in his quarters, between artillery calculations and military duties, he set himself a specific problem. What does spacetime look like around a perfectly spherical, non-rotating mass? It was the simplest possible scenario, an idealized case that didn't exist anywhere in nature. But if he could solve it, the solution might provide insights into more realistic situations. Incredibly, within weeks, Schwarzschild found an exact solution to Einstein's field equations. He sent his paper to Einstein in late 1915, and it was presented to the Prussian Academy in January 1916. Einstein was astonished. He had believed finding exact solutions would be virtually impossible, and here was Schwarzschild, working from a war zone, handing him the first complete solution to the field equations. The Schwarzschild solution, as it came to be known, describes the geometry of spacetime around a spherically symmetric mass. It introduced a crucial quantity now called the Schwarzschild radius. For any given mass, there exists a critical radius at which something very strange happens. If all the mass were compressed within this radius, the curvature of spacetime becomes so extreme that the escape velocity at that radius exactly equals the speed of light. For an object the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it's only about 9 millimeters. In other words, if you could somehow crush the Sun down to a ball 6 kilometers across, or compress Earth to the size of a marble, spacetime around these objects would become so severely warped that not even light could escape from inside that radius. An event horizon would form, a one-way boundary separating the inside from the outside universe. Schwarzschild himself didn't believe this was physically meaningful. He viewed it as a mathematical curiosity, an artifact of an idealized situation that could never occur in nature. Einstein agreed. The idea that matter could actually collapse to such densities seemed absurd, impossible. Surely some physical process would prevent such an extreme outcome. Tragically, Schwarzschild never lived to see how his solution would transform astrophysics. While on the Russian front, he contracted pemphigus, a rare and painful autoimmune disease that causes blistering of the skin. He was sent home in March 1916, and despite the best medical care available, he died on May 11, 1916, at the age of only 42. In the span of just a few months, he had made a contribution that would echo through the century and beyond. In the years following Schwarzschild's death, physicists studied his solution intensely. They explored its mathematical properties, traced the behavior of light and matter near the Schwarzschild radius, and discovered increasingly strange implications. At the Schwarzschild radius, time itself seemed to slow to a stop from the perspective of a distant observer. Objects falling toward this boundary would appear to freeze, taking an infinite amount of time to actually cross it, though from the perspective of the falling object, nothing special happened at that moment. Most physicists remained skeptical that such objects could exist. The mathematics was clear, but nature surely had other ideas. Through the 1920s and 1930s, the study of stellar structure revealed how stars support themselves against gravitational collapse. Nuclear fusion in their cores generates enormous outward pressure, balancing the inward pull of gravity. When fusion ceases, quantum mechanical effects provide support. For stars below a certain mass, degeneracy pressure, a quantum effect preventing particles from occupying the same state, creates stable configurations called white dwarfs or neutron stars. But what about really massive stars? In 1931, Subrahmanyan Chandrasekhar, a young Indian physicist, calculated that there was an upper limit to the mass of a white dwarf, about 1.4 times the mass of the Sun. Above this limit, degeneracy pressure couldn't support the star. In 1939, J. Robert Oppenheimer and his student Hartland Snyder performed similar calculations for neutron stars, finding a limit of about 2 to 3 solar masses. What would happen to a star whose core exceeded these limits? Oppenheimer and Snyder followed the mathematics to its conclusion. The star would undergo complete gravitational collapse, crushing down past the neutron star stage into something else entirely. They published their findings in September 1939, just as World War II broke out in Europe. Their paper described, for the first time, the formation of what we would now call a black hole. Yet even with this theoretical foundation, few physicists took the idea seriously. Black holes seemed too exotic, too bizarre. They violated intuition. How could something simply vanish from the universe, sealed off behind an event horizon? The suggestion felt more like science fiction than science. It would take decades, new observations, and the work of brilliant theorists like John Wheeler, Roger Penrose, and Stephen Hawking before the scientific community fully embraced black holes as real astrophysical objects. But the seeds had been planted, first by a country rector imagining dark stars, then by a soldier scientist solving equations by candlelight on a distant battlefield, and finally by physicists who followed the logic of general relativity to its most extreme conclusion. The revolution was underway, even if most people didn't realize it yet. If you were to encounter a black hole in space, you wouldn't see a solid object. You wouldn't see a surface, or a boundary marked with warning signs. What you would see, assuming there was nearby light to illuminate it, would be a region where spacetime is so distorted that it creates a distinctive silhouette against the background of stars and glowing gas. To understand what a black hole truly is, we need to explore its structure piece by piece, layer by layer. At the very center lies the singularity. This is not a place in the conventional sense. It's a point, or in some cases a ring, where matter is compressed to infinite density and spacetime curvature becomes infinite. All the mass that formed the black hole, and any additional matter that has fallen in, exists here in a form we cannot comprehend. The laws of physics as we currently understand them break down at the singularity. General relativity, which so accurately describes the rest of the black hole, encounters equations that blow up, producing infinite values that indicate the theory is no longer adequate. Some physicists believe the singularity is a signal that we need a quantum theory of gravity, a framework that merges general relativity with quantum mechanics. Such a theory might reveal that the singularity isn't truly a point of infinite density but rather something else, something finite and governed by quantum laws. But we don't yet have such a theory, so the singularity remains deeply mysterious, a place where our understanding simply stops. Surrounding the singularity, at a distance determined by the black hole's mass, is the event horizon. This is perhaps the most important feature of a black hole, the boundary that gives it its defining characteristic. The event horizon is not a physical surface. There's nothing solid there, no membrane or barrier. It's simply the point of no return, the distance from the singularity inside which the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing inside the event horizon can escape to the outside universe. Light itself, the fastest thing in existence, emitted just inside the horizon, is dragged back toward the singularity. Matter, energy, information, all are trapped. From the outside, the event horizon appears as a perfect black sphere, or in the case of a rotating black hole, a flattened sphere. Light can approach the horizon, orbit around it, or be captured by it, but it cannot come out from within it. The size of the event horizon depends solely on the black hole's mass. For a non-rotating black hole, the Schwarzschild radius defines the horizon. Double the mass, and you double the radius. A black hole with the mass of our Sun would have an event horizon about 6 kilometers across. The supermassive black hole at the center of our Milky Way galaxy, with a mass of about 4 million suns, has an event horizon roughly 24 million kilometers in diameter, about 17 times the size of our Sun. For rotating black holes, which constitute the vast majority of black holes in the universe since most stars rotate, the situation becomes more complex. The solution to Einstein's equations for a rotating mass was found by Roy Kerr in 1963, and it revealed additional structure. A rotating black hole drags spacetime around with it, an effect called frame dragging. Imagine spacetime as a fluid surrounding the black hole. As the black hole spins, it stirs this fluid, forcing it to rotate as well. Close to the black hole, this effect is so strong that nothing can remain stationary. Everything must orbit in the direction of the black hole's rotation, even light itself. The region where this occurs is called the ergosphere. It's located outside the event horizon, forming a flattened ellipsoidal shape around the black hole. Within the ergosphere, you could still escape, but you'd have to work hard, expending energy to move against the dragging of spacetime. At the inner boundary of the ergosphere, which coincides with the event horizon at the poles, the frame dragging becomes absolute. The ergosphere has fascinating theoretical implications. According to a process called the Penrose process, proposed by Roger Penrose in 1969, it's theoretically possible to extract energy from a rotating black hole. If you were to carefully drop an object into the ergosphere at just the right angle and velocity, you could cause it to split into two pieces, with one piece falling into the black hole and the other escaping with more energy than you started with. The extra energy comes from the rotational energy of the black hole itself, which slows down slightly as a result. This is pure theoretical physics, far beyond any practical application, but it demonstrates that black holes aren't completely black. They can, in principle, give up energy. For a Kerr black hole, the singularity is not a point but a ring. If you could somehow survive falling through the event horizon and approach the singularity, you might, in principle, pass through the ring rather than hitting it directly. What would you find on the other side? The mathematics suggests bizarre possibilities such as wormholes connecting to other regions of spacetime or even other universes, but these solutions are generally considered unphysical, artifacts of the idealized mathematics rather than descriptions of reality. There are also charged black holes, described by the Reissner-Nordstrom solution for a non-rotating charged black hole, or the Kerr-Newman solution for a rotating charged black hole. These possess electric charge, which adds additional complexity to the spacetime geometry. However, charged black holes are thought to be rare in nature. Any significant electric charge would quickly be neutralized by attracting opposite charges from the surrounding environment. Most astrophysical black holes are well described by the Kerr solution. They have mass and angular momentum but negligible charge. This leads to an important principle in black hole physics known as the Noether theorem. It states that once a black hole forms, all information about the matter that formed it, except for three quantities, is lost. Those three quantities are mass, angular momentum, and electric charge. Everything else, the chemical composition, the shape, the texture, all the details that would distinguish one chunk of matter from another, disappears. Black holes have no hair, no distinguishing features beyond these three numbers. This raises profound questions about information. If you dropped a library full of books into a black hole, all the information in those books would seemingly vanish from the universe, leaving behind only a slight increase in the black hole's mass. This information paradox has troubled physicists for decades and remains an active area of research. But let's return to the horizon itself. What would you experience if you fell into a black hole? For a small black hole, with a mass similar to a star, the tidal forces near the horizon would be catastrophic. Tidal forces arise because gravity decreases with distance. Your feet, being closer to the black hole than your head, would experience stronger gravitational pull. This difference, stretched across the length of your body, would rip you apart long before you reached the horizon, a process gruesomely dubbed spaghettification by physicists who apparently have a dark sense of humor. For a supermassive black hole, like those at the centers of galaxies, the situation is quite different. The horizon of such a black hole is so large that the curvature of spacetime near it is relatively gentle. You could, in principle, cross the event horizon without experiencing anything unusual. You wouldn't see a sign, wouldn't feel a barrier. To you, space would still seem normal, and you could still see light from the outside universe, though increasingly distorted and redshifted. Only after crossing the horizon would the true horror of your situation become apparent. No matter which direction you pointed your rockets, no matter how powerful your engines, you could not escape. All paths through spacetime would lead inward, toward the singularity. Time and space, in a sense, trade places inside a black hole. Just as you inevitably move forward in time in normal space, inside the event horizon, you inevitably move inward in space, toward the singularity. Your future is the singularity, and nothing can prevent it. From the outside universe, observers would never see you cross the horizon. As you fell, light from your spacecraft would become increasingly redshifted, shifting toward longer and longer wavelengths, while the rate at which light reaches distant observers would slow down. You would appear to freeze at the horizon, your image dimming and reddening until you faded from view entirely. But this is an illusion created by the extreme warping of spacetime. From your perspective, you'd cross the horizon in finite time, though that would be little comfort given what awaited you on the other side. This anatomy, the singularity, the event horizon, the ergosphere, frame dragging, all emerge from pure mathematics, from solving Einstein's equations for extreme conditions. Yet these aren't merely theoretical constructs. We now have direct observational evidence that objects matching these descriptions exist in our universe. They're out there, lurking in the darkness, warping spacetime around them, and occasionally revealing their presence through the effects they have on their surroundings. Black holes don't spring into existence fully formed. They're born, though their births are among the most violent events in the cosmos. To understand how black holes form, we need to first understand the life cycle of stars, for it's in the deaths of massive stars that most black holes are created. Stars are born from vast clouds of gas, primarily hydrogen, floating in space. When a region of such a cloud becomes dense enough, gravity takes over, pulling the gas inward. As the cloud contracts, it heats up. Eventually, the core becomes so hot and dense that nuclear fusion ignites. Hydrogen atoms are forced together to form helium, releasing enormous amounts of energy in the process. This energy creates pressure that pushes outward, counterbalancing gravity's inward pull. A star is born. For most of a star's life, it exists in this state of balance, called hydrostatic equilibrium. The outward pressure from fusion exactly matches the inward pull of gravity. Our Sun has been in this state for about 5 billion years and will remain so for another 5 billion. The more massive a star, however, the shorter its life. Massive stars burn through their fuel much faster, living only millions of years rather than billions. As a star ages, it exhausts the hydrogen in its core. What happens next depends on the star's mass. For stars like our Sun or smaller, the outer layers expand into a red giant, while the core, unable to sustain fusion, contracts and becomes a white dwarf, a dense ember supported by electron degeneracy pressure. These stars never become black holes. They simply aren't massive enough. For stars with masses above about 8 to 10 times that of the Sun, the story is different. When hydrogen fusion ceases in the core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. This provides a new source of energy, temporarily halting the collapse. But helium fusion doesn't last long. When the helium is exhausted, if the star is massive enough, the core contracts again and reaches temperatures that allow carbon fusion, then oxygen fusion, then neon, then silicon. Each successive stage of fusion is shorter than the last. A star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, but only days fusing silicon. The core develops a layered structure like an onion, with each shell fusing different elements, and at the very center, iron accumulates. Iron is the end of the line. Fusing iron doesn't release energy, it consumes energy. A core made of iron cannot support itself through fusion. When the iron core reaches about 1.4 solar masses, the Chandrasekhar limit, it can no longer withstand the crushing force of gravity. In less than a second, the core collapses. This collapse is incredibly rapid. The core, roughly the size of Earth, shrinks to a sphere about 20 kilometers across in less time than it takes to blink. Matter, protons and electrons, is squeezed so tightly that they merge into neutrons. A shock wave blasts outward, tearing through the star's outer layers. The star explodes in a supernova, one of the brightest events in the universe, briefly outshining entire galaxies. What remains depends on the mass of the core. If the core is between about 1.4 and 2.5 solar masses, it becomes a neutron star, a ball of neutrons held up by neutron degeneracy pressure. Neutron stars are extraordinary objects in their own right, with densities so extreme that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. But if the core is more massive, above the Tolman-Oppenheimer-Fokoff limit of approximately 2 to 3 solar masses, even neutron degeneracy pressure cannot stop the collapse. No known force in physics can halt it. The core continues to contract, becoming smaller and smaller, denser and denser, until it crosses its own Schwarzschild radius. An event horizon forms. A black hole is born. This process, the collapse of a massive star's core, is how stellar mass black holes form. These black holes typically have masses between about 3 and 20 times the mass of the Sun, though some can be more massive depending on the original star's size and how much mass was lost during the supernova. Stellar mass black holes are relatively common. In our Milky Way galaxy alone, astronomers estimate there may be tens of millions to perhaps 100 million stellar mass black holes, the remnants of massive stars that lived and died over the galaxy's 10 billion year history. Most of these black holes are solitary, drifting through space, invisible unless they happen to pass near a star or gas cloud. But stellar collapse isn't the only way black holes can form. In the early universe, conditions may have allowed for the creation of primordial black holes. In the first fractions of a second after the Big Bang, the universe was incredibly dense and hot. Quantum fluctuations in density could have created regions that were compressed enough to collapse directly into black holes, without needing to go through the stellar life cycle. Primordial black holes could theoretically have any mass, from tiny, less than the mass of a mountain, to millions of times the mass of the Sun. If they exist, very small primordial black holes would have evaporated by now due to Hawking radiation, but larger ones could still be out there. Some scientists have even speculated that primordial black holes might constitute part or all of the mysterious dark matter that makes up most of the mass in the universe. However, no primordial black holes have been definitively detected, and they remain hypothetical. Then there are the supermassive black holes. These are the giants, with masses ranging from hundreds of thousands to billions of times the mass of the Sun. Almost every large galaxy, including our own, has a supermassive black hole at its center. How these behemoths formed is one of the great unsolved mysteries in astrophysics. The problem is timing. Astronomers have found supermassive black holes in galaxies that formed less than 1 billion years after the Big Bang. That doesn't seem like enough time for a normal black hole, formed from stellar collapse, to grow so massive. Even if such a black hole swallowed everything in its vicinity, the rate at which it could accrete mass is limited by physical processes. Gas falling into a black hole heats up and radiates energy, creating pressure that pushes other gas away, regulating the feeding rate. To grow from a stellar mass black hole to 1 billion solar masses in less than 1 billion years seems to require feeding at rates faster than this limit allows. Several theories attempt to explain supermassive black hole formation. One idea is that they formed from the direct collapse of massive gas clouds in the early universe. Under special conditions, with little or no metal content and minimal cooling, a gas cloud might collapse directly into a black hole with tens of thousands or even hundreds of thousands of solar masses, giving it a substantial head start. These seed black holes could then grow more quickly to supermassive sizes. Another possibility is that supermassive black holes formed from the mergers of many smaller black holes. In the dense stellar environments of the early universe, black holes might have sunk to the centers of star clusters, merged with each other, and gradually built up mass. Computer simulations show this process can create intermediate mass black holes, with masses between stellar mass and supermassive, which might then merge and grow further. There's also the idea that the first generation of stars, called population 3 stars, were much more massive than stars today, perhaps up to several hundred times the mass of the Sun. These massive stars would have lived very short lives and collapsed into large black holes when they died, creating seeds for supermassive black holes. The truth is, we don't know for certain how supermassive black holes form. It's likely that multiple processes contribute. Some may form from direct collapse, others from mergers, and still others from particularly massive stars. Ongoing observations with telescopes like the James Webb Space Telescope are pushing back to the earliest epochs of the universe, finding supermassive black holes and studying how they evolve, hoping to solve this cosmic puzzle. Intermediate mass black holes, those between stellar mass and supermassive, are particularly mysterious. Theory predicts they should exist either as seeds for supermassive black holes or as products of stellar mergers in dense clusters. But confirmed detections are rare. A few candidates have been found, lurking in dense globular clusters or in the centers of dwarf galaxies, but the evidence is often ambiguous. If they exist in large numbers, we haven't found them yet, and if they're rare, we need to understand why. What we do know is that black holes, once formed, are remarkably stable. Unlike stars, which burn through their fuel and evolve, a black hole can persist essentially unchanged for extraordinary lengths of time. It can grow by accreting matter, or it can merge with other black holes, but absent these external influences, it simply exists, a permanent scar on spacetime, a testament to gravity's ultimate victory over all other forces. Not all black holes are created equal. Over decades of theoretical work and observation, scientists have identified several distinct categories of black holes, each with not all black holes are created equal. Over decades of theoretical work and observation, scientists have identified several distinct categories of black holes, each with its own characteristics, formation mechanisms, and roles in the cosmic drama. Think of it as a zoo, though instead of observing animals behind glass, we're cataloging objects so extreme they defy direct observation. The smallest members of this zoo are the stellar mass black holes. These are the corpses of massive stars, the final stage of stellar evolution for stars born with more than about 20 times the mass of the Sun. Stellar mass black holes typically range from about 3 solar masses, the minimum required to overcome neutron degeneracy pressure, up to perhaps 100 solar masses, though most fall between 5 and 20 solar masses. These black holes are scattered throughout galaxies, invisible except when circumstances reveal their presence. A solitary stellar mass black hole, drifting through the emptiness between stars, is essentially undetectable with current technology. It emits no light, produces no radiation, and is too small to gravitationally lens background stars in a noticeable way. Astronomers estimate our Milky Way might contain 100 million such black holes, silent and invisible, remnants of stars that died billions of years ago. We detect stellar mass black holes primarily when they exist in binary systems, orbiting a normal star. If the orbit is close enough, the black hole's gravity can strip gas from its companion star. This gas doesn't fall directly into the black hole. Instead, it spirals inward, forming a structure called an accretion disk. We'll explore accretion disks in detail later, but for now, the key point is that the disk heats to millions of degrees, hot enough to emit intense X-rays. These X-ray binary systems are beacons, announcing the presence of black holes to our telescopes. The first strong black hole candidate discovered this way was Cygnus X-1, found in 1964 when X-ray detectors were flown on sounding rockets. Cygnus X-1 is a bright X-ray source in the constellation Cygnus, the Swan. Optical observations revealed it was associated with a massive blue supergiant star called HDE 226868. The star exhibited a wobble, indicating it was orbiting an unseen companion. By studying the orbital motion, astronomers calculated the companion's mass at about 15 times the mass of the Sun, far too massive to be a neutron star. The evidence strongly suggested a black hole. For years, debate raged about whether Cygnus X-1 was truly a black hole or some exotic type of star. In 1974, Stephen Hawking made a famous bet with fellow physicist Kip Thorne. Hawking bet that Cygnus X-1 was not a black hole, a position he later described as an insurance policy. If it turned out not to be a black hole, at least he'd win the bet. The evidence accumulated over the years, and in 1990, Hawking conceded, giving Thorne a subscription to Penthouse magazine, as specified in the bet's terms. Science can be delightfully strange sometimes. Since then, dozens of stellar mass black holes have been identified in X-ray binary systems. Each discovery has refined our understanding of these objects. We've learned that they can spin at extraordinary rates, approaching the maximum allowed by general relativity, where the event horizon rotates at nearly the speed of light. We've measured their masses, studied the behavior of matter falling into them, and confirmed that they match theoretical predictions with remarkable precision. Recently, gravitational wave astronomy has opened an entirely new window into stellar mass black holes. When two black holes orbit each other, they emit gravitational waves, ripples in spacetime itself. As they radiate this energy, they gradually spiral closer together, orbiting faster and faster, until they finally merge in a cataclysmic collision. The merger produces a burst of gravitational waves strong enough to be detected by instruments on Earth, even when the collision occurs billions of light-years away. The first detection, announced in February 2016 by the LIGO collaboration, came from two black holes with masses around 30 times the Sun, located over 1 billion light-years away. They spiraled together and merged, releasing more energy in gravitational waves during the final fraction of a second than all the stars in the visible universe emitted as light during that same time. It was a momentous discovery, confirming Einstein's prediction of gravitational waves and opening a new era in astronomy. Since that first detection, dozens more black hole mergers have been observed. These detections have revealed surprising things. Some black holes are more massive than expected, challenging theories of stellar evolution. Some mergers produce black holes spinning in unexpected directions, suggesting complex formation histories. Gravitational wave astronomy is still in its infancy, but it's already revolutionizing our understanding of stellar mass black holes. At the opposite end of the scale are the supermassive black holes, the true giants of the zoo. These monsters reside at the centers of most galaxies, including our own. Their masses range from hundreds of thousands to tens of billions of times the mass of the Sun. The largest known supermassive black hole, as of current observations, is TON 618, with an estimated mass of around 66 billion solar masses, located over 10 billion light-years away. Its event horizon would be about 40 times the distance from the Sun to Neptune. It's difficult to comprehend such scales. Supermassive black holes are central to galaxy evolution. The relationship between a galaxy's central black hole and the galaxy itself is remarkably tight. The black hole's mass correlates strongly with the mass of the galaxy's central bulge and with the velocities of stars in the bulge. This suggests that galaxies and their central black holes grow together, influencing each other through a process called coevolution. When supermassive black holes actively feed on surrounding gas, they become active galactic nuclei, or AGN. The accretion disk around such a black hole can outshine the entire galaxy, radiating across the electromagnetic spectrum from radio waves to gamma rays. The most luminous AGN are called quasars, and they were far more common in the early universe than they are today. Observing distant quasars is like looking back in time to when the universe was young and gas was more plentiful, feeding these black holes and making them blaze with incredible brightness. Our own galaxy's central supermassive black hole is relatively quiet. It's called Sagittarius A*, pronounced Sagittarius A*, named for its location in the constellation Sagittarius. Its mass is approximately 4 million times that of the Sun, modest by supermassive standards. While it occasionally flares in X-rays as small amounts of gas fall in, it's not currently an AGN. It's a sleeping giant, and we should be grateful. An actively feeding supermassive black hole at the center of the Milky Way would flood the galaxy with radiation, potentially making life on planets like Earth much more difficult. Between stellar mass and supermassive black holes lies a mysterious gap, the realm of intermediate mass black holes. These would have masses from about 100 to 100,000 times the mass of the Sun. Theory suggests they should exist, yet confirmed detections are frustratingly rare. Several candidates have been proposed. Some dense star clusters show velocity patterns suggesting a black hole with thousands of solar masses at their center. Certain ultraluminous X-ray sources, which are too bright to be powered by stellar mass black holes but not bright enough to be supermassive black holes, might be intermediate mass black holes accreting gas. A few tidal disruption events, where a star is torn apart by a black hole's gravity, have been observed with properties suggesting intermediate mass black holes. Gravitational wave observations have provided perhaps the strongest evidence. Some detected mergers involve black holes in the lower end of this range, around 100 solar masses. These are too massive to form easily from single stellar collapse but too small to be supermassive. They might be the products of earlier black hole mergers in dense stellar environments, each generation building to larger masses. The scarcity of intermediate mass black holes is puzzling. If supermassive black holes grow from smaller seeds, where are all the intermediate stages? One possibility is that they grow very quickly, spending little time in this mass range. Another is that they're simply hard to detect. Unlike stellar mass black holes, they're unlikely to have binary companions, and unlike supermassive black holes, they're not sitting in easily identifiable galaxy centers. They might be lurking in dwarf galaxies, in wandering orbits within larger galaxies, or in other hard-to-search locations. Then there are the theoretical exotic black holes. Primordial black holes, if they exist, could span an enormous range of masses. Micro-black holes, far smaller than an atom, could have formed in the early universe's extreme conditions. These would have evaporated long ago due to Hawking radiation. Larger primordial black holes, however, could still exist. If dark matter consists partially or entirely of primordial black holes, they might be extremely numerous, though individually too small to be easily detected. Some theories propose that microscopic black holes could be created in high-energy particle collisions, such as those at the Large Hadron Collider. These hypothetical black holes would be governed by physics beyond general relativity, possibly involving extra dimensions predicted by string theory. If they formed, they would evaporate essentially instantaneously through Hawking radiation, leaving characteristic signatures in the particle debris. Despite extensive searches, no evidence for such black holes has been found, which places important constraints on these theoretical models. There are also maximally rotating black holes, called extremal Kerr black holes, spinning at the theoretical maximum rate. In such a black hole, the inner and outer event horizons merge into a single surface, and the singularity becomes a ring rather than a point. Whether such black holes actually exist in nature is uncertain. Astrophysical processes that form black holes, such as stellar collapse or mergers, generally produce black holes with some rotation but not necessarily maximal rotation. Finally, there are binary black hole systems and potentially even systems with 3 or more black holes orbiting each other. These are dynamic, evolving systems. The black holes spiral together over time due to gravitational wave emission, eventually merging into a single larger black hole. Some galaxies might have 2 supermassive black holes at their centers, the result of a galaxy merger. These dual supermassive black holes would eventually merge, producing gravitational waves far stronger than those from stellar mass black hole mergers, though with frequencies too low for current detectors to observe. Each type of black hole, from the smallest stellar remnants to the largest supermassive giants, plays a role in the cosmos. They're not mere curiosities or cosmic dead ends. They're active participants in cosmic evolution, influencing star formation, regulating galaxy growth, and serving as cosmic laboratories where the laws of physics are pushed to their limits. Understanding this zoo of black holes, in all its variety and strangeness, is essential to understanding the universe itself. A black hole is not just a passive object sitting in space. It's a dynamic entity that interacts with its environment in spectacular ways. The region around a black hole, especially one that's actively feeding, is one of the most energetic and violent places in the universe. To understand what happens near a black hole, we need to explore several key phenomena, each more remarkable than the last. Let's begin with accretion, the process by which a black hole feeds. A solitary black hole, with nothing nearby to consume, is essentially inert. But place a black hole near a source of matter, a companion star, a gas cloud, or debris from a disrupted planet, and things become interesting. Matter falling toward a black hole doesn't simply plunge straight in. Because the matter typically has some angular momentum, some sideways motion, it instead spirals inward, forming a rotating disk around the black hole called an accretion disk. This disk is not a solid structure but rather a swirling collection of gas, dust, and plasma orbiting at different speeds depending on distance from the black hole. The inner regions of the disk orbit much faster than the outer regions. This difference in orbital speed creates friction between adjacent rings of material. Particles rub against each other, colliding and transferring energy. This friction heats the disk to extraordinary temperatures. Close to the black hole, the disk can reach temperatures of millions or even billions of degrees, hot enough to emit X-rays and gamma rays. An accretion disk around a stellar mass black hole is relatively small, perhaps a few thousand kilometers across at most. Around a supermassive black hole, the disk can be light-years in diameter. Despite their size differences, the physical processes are similar. Gas spirals inward, friction heats it up, and it radiates energy before finally crossing the event horizon and disappearing forever. The amount of energy released by accretion is staggering. According to Einstein's famous equation, energy equals mass times the speed of light squared. When matter falls into a black hole, a significant fraction of its rest mass energy can be converted into radiation, up to about 10% for a rapidly rotating black hole. For comparison, nuclear fusion in stars converts less than 1% of mass into energy. Accretion onto black holes is the most efficient energy generation process known in nature. This efficiency explains why active galactic nuclei and quasars can be so luminous. A supermassive black hole swallowing just a few solar masses of gas per year can outshine an entire galaxy of hundreds of billions of stars. The central black hole in a quasar, though minuscule compared to the galaxy surrounding it, can release more energy than all those stars combined. But accretion disks do more than just radiate. They also produce jets, highly collimated streams of matter and energy that blast outward from the black hole's poles at speeds approaching the speed of light. These jets can extend for thousands or even millions of light-years, punching through the galaxy and far out into intergalactic space. The exact mechanism by which jets form is still debated, but the general picture involves magnetic fields. As gas in the accretion disk spirals inward, it carries magnetic field lines with it. These field lines become twisted and amplified, creating a powerful magnetic structure threading through the disk and surrounding the black hole. Matter and energy can be channeled along these magnetic field lines, funneled away from the disk in narrow beams shooting perpendicular to the disk's plane. The energy for these jets likely comes from both the accretion disk and the rotational energy of the black hole itself. In the ergosphere of a rotating black hole, magnetic field lines can tap into the black hole's spin, extracting rotational energy through a process called the Blandford's-Najek mechanism. This energy is then carried away by particles streaming along the magnetic fields, creating the jets. Jets from supermassive black holes in galaxy clusters can have profound effects on their surroundings. They pump enormous amounts of energy into the intergalactic medium, heating gas and preventing it from cooling and forming stars. This feedback process, where the black hole regulates its own fuel supply by heating nearby gas, is thought to be crucial for understanding why the most massive galaxies stopped forming stars billions of years ago. Another phenomenon associated with black holes is gravitational lensing. Because black holes warp spacetime so severely, light passing near them follows curved paths. If a black hole passes between us and a more distant light source, such as a star or galaxy, the black hole's gravity can bend the light from that source, distorting or magnifying its image. For a perfectly aligned black hole and background source, the result is an Einstein ring, a circle of light surrounding the black hole's silhouette. More typically, the alignment isn't perfect, and you see multiple distorted images of the background object, or arcs of light. Gravitational lensing by black holes has been observed, though it's more commonly associated with galaxies or galaxy clusters, which contain far more mass and produce stronger lensing effects. Microlensing events occur when a stellar mass black hole passes in front of a distant star. The black hole's gravity briefly magnifies the star's light, causing a temporary brightening that can last days or weeks. By studying these events, astronomers can detect isolated black holes that would otherwise be invisible. Several microlensing surveys have found events that might be caused by black holes, though distinguishing them from other massive objects can be challenging. Close to a black hole, the warping of spacetime produces optical effects that would be utterly bizarre to witness. Light orbits around the black hole in a structure called the photon sphere, located at 1.5 times the Schwarzschild radius for a non-rotating black hole. Photons traveling exactly at this distance can orbit indefinitely, though the orbit is unstable. Any slight perturbation will cause the photon to either escape to infinity or spiral into the black hole. If you somehow found yourself orbiting just outside the photon sphere, looking toward the black hole, you would see a dark sphere, the black hole's shadow, which is about 2.6 times the Schwarzschild radius in size. This shadow is not the event horizon itself but rather the region from which no light can escape to reach your eyes. Behind the black hole, you would see light from distant stars and the accretion disk, but distorted and multiplied. Light from the disk could wrap around the black hole multiple times before reaching you, creating a series of increasingly compressed and distorted images stacked around the black hole's edge. The disk would appear to extend both above and below the black hole, even though it's actually confined to the equatorial plane, because the black hole's gravity bends light from behind the black hole up and over it to your eyes. Colors would be shifted dramatically. Light coming from gas moving toward you would be blue shifted, appearing bluer and brighter, while light from gas moving away would be red shifted, appearing redder and dimmer. The combination of gravitational redshift, caused by light climbing out of the deep gravitational well, and Doppler shifts, caused by the disk's rotation, creates complex patterns of brightness and color across the disk. Frame dragging effects would also be visible. Near a rotating black hole, space itself is dragged around in the direction of the black hole's rotation. The inner edge of the accretion disk, where frame dragging is strongest, rotates at a substantial fraction of the speed of light. Matter in the disk experiences extreme forces, tidal stresses, and magnetic turbulence, all contributing to the disk's heat and luminosity. Finally, there are tidal disruption events, violent phenomena that occur when a star wanders too close to a black hole. Each object has a tidal radius, the distance at which tidal forces from another object overcome the first object's self-gravity. For a star approaching a supermassive black hole, there's a distance where the difference in gravitational pull between the star's near side and far side exceeds the star's ability to hold itself together. When this happens, the star is literally torn apart. It's stretched into a long stream of gas, a process that takes hours or days. Half of the star's material gains enough energy to escape the black hole entirely, flying off into space. The other half remains bound and falls back toward the black hole, colliding with itself and forming a rapidly accreting debris disk. The result is a brilliant flare of light, primarily in ultraviolet and X-ray wavelengths, that can last months or years as the stellar debris is consumed. Astronomers have detected dozens of these tidal disruption events, each providing a unique opportunity to study black holes that are otherwise dormant. The flare's properties, its brightness, spectrum, and evolution, reveal information about both the star that was destroyed and the black hole that destroyed it. All these phenomena, from accretion disks to jets to gravitational lensing to tidal disruptions, demonstrate that black holes are far from the simple, static objects they might seem at first. They're dynamic, active, and deeply connected to their surroundings. They shape galaxies, launch material across cosmic distances, and create some of the most extreme conditions in the universe. Understanding these dynamics is crucial to understanding how black holes fit into the broader cosmic picture. For decades after their theoretical prediction, black holes were seen as one-way streets. Matter and energy fell in, and nothing came out. The event horizon was absolute, an impenetrable barrier from which no escape was possible. Then, in 1974, a young British physicist named Stephen Hawking published a paper that fundamentally changed this view. He showed that black holes aren't completely black after all. They emit radiation, they have temperature, and eventually, they evaporate. To understand Hawking radiation, we need to combine two theories that don't normally play well together: general relativity, which describes gravity and spacetime, and quantum mechanics, which governs the behavior of particles at the smallest scales. Hawking's insight came from considering quantum effects near a black hole's event horizon. In quantum field theory, what we think of as empty space isn't truly empty. The vacuum is filled with quantum fluctuations, brief disturbances in energy that constantly create and destroy virtual particle-antiparticle pairs. Normally, these pairs appear, exist for a fleeting instant, and then annihilate each other, vanishing back into the vacuum. The process happens everywhere, all the time, but it has no observable effect in ordinary circumstances. Near a black hole's event horizon, something different can happen. Imagine a virtual particle pair appearing just outside the horizon. Normally, they would quickly annihilate. But if one particle falls across the horizon before annihilation can occur, the pair is separated. The particle inside the horizon is lost forever, but the particle outside can escape to infinity. From a distant observer's perspective, it appears that the black hole has emitted a particle. To conserve energy, the particle that fell in must have had negative energy from the black hole's perspective. This means the black hole loses a tiny amount of mass each time a particle escapes. The black hole is slowly evaporating, converting its mass into radiation. This radiation is called Hawking radiation, and it has a thermal spectrum. That means it's identical to the radiation emitted by a hot object, with a temperature determined by the black hole's mass. The smaller the black hole, the higher its temperature. A black hole with the mass of the Sun would have a temperature of about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation left over from the Big Bang. Such a black hole would absorb more energy from the background radiation than it emits, so it would actually grow slightly. But consider a much smaller black hole, say one with the mass of a mountain. Its temperature would be billions of degrees. It would radiate intensely, glowing brighter than any star, and evaporate completely within a fraction of a second in a final explosion of energy. The rate of evaporation depends on mass. More massive black holes evaporate more slowly. A stellar mass black hole would take about 10 to the power of 67 years to evaporate, an incomprehensibly long time, far longer than the current age of the universe. A supermassive black hole would take even longer, on the order of 10 to the power of 100 years or more. For all practical purposes, astrophysical black holes we observe today are not evaporating. The universe is still too young and too warm. But in the far distant future, long after stars have ceased to shine and galaxies have dispersed, black holes will be among the last remaining structures. And even they will eventually evaporate, leaving behind only a cold, dilute sea of particles and radiation. Hawking's discovery had profound implications beyond just black hole evaporation. It revealed that black holes have thermodynamic properties, like temperature and entropy. Entropy is a measure of disorder or the number of possible microscopic states consistent with a system's macroscopic properties. The second law of thermodynamics states that entropy always increases in an isolated system. Before Hawking, there was a puzzle. If you dropped a hot object into a black hole, the object's entropy would seem to disappear, violating the second law. But Jacob Bekenstein, building on earlier insights, proposed that black holes themselves have entropy, proportional to the surface area of their event horizon. When matter falls into a black hole, the black hole's horizon grows, increasing its entropy by more than the entropy of the infalling matter. The total entropy increases, and the second law is preserved. Hawking radiation confirmed this idea. A black hole with temperature must have entropy, and Hawking's calculation showed that the entropy is indeed proportional to the horizon area. The formula for black hole entropy is elegantly simple: entropy equals 1/4 the horizon area in Planck units. This connection between gravity, quantum mechanics, and thermodynamics is one of the deepest insights in theoretical physics. But Hawking radiation also created a new puzzle, the black hole information paradox. In quantum mechanics, information is never destroyed. The state of a system evolves over time, but you can, in principle, always reconstruct past states from the present state. Information is preserved. Now imagine throwing a book into a black hole. The book contains information, the arrangement of atoms on each page, the specific words and sentences. Once the book crosses the horizon, that information seems lost to the outside universe. The black hole might grow slightly, but all information about what fell in is hidden behind the horizon. As the black hole evaporates via Hawking radiation, it shrinks. Eventually, it vanishes completely. The radiation it emitted during evaporation is thermal, random, containing no information about what fell in. So where did the information go? Was it destroyed, violating quantum mechanics? Is it somehow encoded in the radiation in a way we don't understand? Does it remain in some remnant left after evaporation? For decades, physicists debated this paradox. Stephen Hawking initially believed that information was truly lost, that black holes provided an exception to quantum mechanics rules. Others, including Leonard Susskind and Gerard T. Hooft, argued that information must be preserved somehow, leading to heated debates. Recent developments suggest the information is not lost but rather encoded in subtle correlations in the Hawking radiation, in ways that require understanding the quantum properties of spacetime itself. The holographic principle, arising from string theory, proposes that all the information about a volume of space can be encoded on its boundary, like a hologram. For a black hole, this means all information about the interior is somehow encoded on the event horizon. The resolution of the information paradox likely requires a complete theory of quantum gravity, which we don't yet have. But the progress made in tackling this problem has led to deep insights about the nature of spacetime, entropy, and information. What began as a calculation about particle creation near black holes has evolved into one of the central problems in theoretical physics, guiding research into string theory, loop quantum gravity, and other approaches to understanding the quantum nature of gravity. Hawking himself, in his later years, conceded that information is probably preserved, though the mechanism remains unclear. In 2004, he famously admitted he was wrong about information loss, settling a bet with fellow physicist John Preskill by giving him an encyclopedia, stating that information could be retrieved from a black hole, though in a practical sense, the information would be useless, like burning an encyclopedia and trying to reconstruct it from the smoke and ashes. The study of black hole thermodynamics continues to reveal surprises. Black holes are the most entropic objects possible for a given volume. They represent maximum entropy configurations. This suggests deep connections between gravity, information, and the fundamental structure of spacetime. Some physicists believe that spacetime itself might be an emergent phenomenon, arising from quantum entanglement and information, with black holes providing crucial clues. What Hawking began with a simple calculation about quantum effects near an event horizon has blossomed into a rich field connecting gravity, quantum mechanics, thermodynamics, and information theory. Black holes, rather than being endpoints where physics breaks down, have become laboratories for exploring the deepest questions about reality. And Hawking radiation, though far too faint to detect from any astrophysical black hole, remains one of the most important theoretical discoveries in modern physics. Black holes present a fundamental challenge: they're invisible. By definition, they emit no light. They're darker than the darkest night, perfect voids against the backdrop of space. So how do astronomers detect and study objects that cannot be seen? The answer lies in observing their effects on surrounding matter and spacetime. Over decades, astronomers have developed increasingly sophisticated techniques for finding black holes and measuring their properties. The first method, and still one of the most important, is studying binary star systems. Many stars exist in pairs, orbiting their common center of mass. If one member of such a binary undergoes supernova collapse and forms a black hole, the system becomes an X-ray binary. As we discussed earlier, the black hole's gravity can pull gas from its companion star. This gas forms an accretion disk and heats to millions of degrees, emitting powerful X-rays. X-ray astronomy began in earnest in the 1960s with rocket-borne detectors that could briefly rise above Earth's atmosphere, which blocks X-rays from space. These early missions discovered intense X-ray sources scattered across the sky. Many turned out to be neutron stars, but some, like Cygnus X-1, were too massive to be anything other than black holes. Later satellites, such as Uhuru, launched in 1970, the first X-ray astronomy satellite, greatly expanded the catalog of X-ray sources. By studying the X-ray emission, its spectrum, variability, and intensity, astronomers could infer properties of the compact object producing it. Rapid variability, flickering on timescales of milliseconds, indicated a small object. Massive objects in binary systems with no visible surface emission suggested black holes rather than neutron stars. Optical observations complement X-ray data. By measuring the orbital motion of the visible star in an X-ray binary, astronomers can calculate the mass of its unseen companion using Kepler's laws. If that mass exceeds the theoretical maximum for a neutron star, about 2 to 3 solar masses, the invisible companion must be a black hole. Dozens of stellar mass black holes have been confirmed this way. More recent surveys have identified black holes through purely optical observations, without requiring X-ray emission. By measuring subtle wobbles in stars' motion caused by unseen companions, surveys like the European Space Agency's Gaia mission have found several black holes. These systems are dormant, with the black hole not actively accreting gas, so they produce no X-ray emission. They're invisible not just in visible light but across the electromagnetic spectrum, revealed only through their gravitational influence. For supermassive black holes at the centers of galaxies, detection methods are different. In our own galaxy, astronomers have tracked the orbits of stars very close to the galactic center. These stars move at extraordinary speeds, some completing orbits in just a few years. By plotting their trajectories over decades, astronomers have precisely determined that they're orbiting an invisible object with a mass of about 4 million suns, confined to a region smaller than our solar system. The only plausible explanation is a supermassive black hole, which we call Sagittarius A star. Andrea Ghez and Reinhard Genzel led the teams that mapped these stellar orbits, work for which they shared the 2020 Nobel Prize in Physics. Their observations provided some of the strongest evidence for supermassive black holes and demonstrated that our galaxy harbors one at its heart. In other galaxies, supermassive black holes are detected through their effects on surrounding gas and stars. The velocities of stars and gas clouds near a galaxy's center reveal the gravitational pull of the central mass. If those velocities are very high, requiring a large mass concentrated in a small volume, a supermassive black hole is the best explanation. Active galaxies, where the central black hole is feeding, are easier to spot. The luminous accretion disk and powerful jets emit radiation across the spectrum, from radio waves to X-rays and gamma rays. Quasars, blazars, and radio galaxies all represent different viewing angles and feeding rates of supermassive black holes. By studying their spectra, luminosity, and variability, astronomers can estimate the black hole's mass, spin, and feeding rate. Then came gravitational wave astronomy, opening an entirely new way to observe black holes. Einstein's general relativity predicts that accelerating masses emit gravitational waves, ripples in spacetime itself that propagate at the speed of light. For most astrophysical situations, these waves are incredibly weak. But when two black holes orbit each other and merge, the gravitational waves become strong enough to detect. The Laser Interferometer Gravitational Wave Observatory, or LIGO, was designed to detect these waves. It consists of two facilities, one in Louisiana and one in Washington state, each with two perpendicular arms 4 kilometers long. Laser beams bounce back and forth along these arms, and when a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction. The effect is tiny, a change in distance smaller than the width of a proton, but LIGO's exquisitely sensitive instruments can measure it. On September 14, 2015, LIGO detected gravitational waves from the merger of two black holes, each about 30 times the mass of the Sun, located over 1 billion light-years away. The signal lasted only a fraction of a second, but it matched theoretical predictions almost perfectly. The discovery, announced in February 2016, was a triumph for physics, confirming Einstein's century-old prediction and providing direct evidence that black holes exist and that they merge. Since then, the LIGO and Virgo collaborations, joined more recently by KAGRA in Japan, have detected dozens of black hole mergers. Each detection provides measurements of the black hole's masses and spins. We've learned that black holes merge frequently, that they span a wide range of masses, and that the final merged black hole rings like a bell, emitting gravitational waves at specific frequencies determined by its mass and spin. Gravitational wave detections have also revealed intermediate mass black holes and confirmed that black hole mergers can produce black holes more massive than could form from single stellar collapse. They've allowed us to test general relativity in the strong field regime, where gravity is most intense, and found that the theory passes every test with remarkable accuracy. Perhaps most impressively, gravitational wave astronomy is completely independent of electromagnetic observations. Gravitational waves pass through matter unimpeded, so we can observe events that would be completely hidden in light. Black hole mergers occurring inside dense gas clouds, or in the early universe when it was opaque to light, are readily detected through their gravitational waves. The future of gravitational wave astronomy is bright. Ground-based detectors continue to improve their sensitivity. Space-based detectors, like the planned Laser Interferometer Space Antenna, or LISA, will detect waves from supermassive black hole mergers, events producing far stronger signals at lower frequencies than ground-based detectors can observe. These mergers occur when galaxies collide, and observing them will teach us about galaxy evolution and the growth of supermassive black holes. But perhaps the most dramatic technique for observing black holes is direct imaging. For decades, this seemed impossible. Even the nearest supermassive black hole, Sagittarius A** at the center of our galaxy, subtends an angle on the sky far too small for conventional telescopes to resolve. To image it would require a telescope with an aperture the size of Earth. Astronomers found a way: Very Long Baseline Interferometry, or VLBI. By combining signals from radio telescopes scattered across the globe, synchronized using atomic clocks, they could create a virtual telescope with Earth-sized aperture. The technique had been used for decades to study radio sources with high resolution, but applying it to black holes required pushing the technology to its limits. The Event Horizon Telescope, or EHT, was designed specifically to image black holes. It's not a single instrument but a collaboration of radio telescopes around the world, from Hawaii to Antarctica, from Europe to South America. When these telescopes observe the same target simultaneously, their data can be combined to create images with resolution comparable to reading a newspaper in New York from Paris, or seeing an orange on the moon. The targets were chosen carefully: Sagittarius A**, the supermassive black hole at the center of our Milky Way, and M87**, an even larger black hole at the center of the giant elliptical galaxy Messier 87, located about 55 million light-years away. Though M87** is much farther than Sagittarius A**, it's also much more massive, about 6.5 billion times the mass of the Sun compared to Sagittarius A**'s 4 million solar masses. From Earth, both black holes appear about the same size on the sky, roughly 40 microarcseconds, perfect targets for the EHT. Over several nights in April 2017, the EHT collected data. Each telescope recorded petabytes of information, far too much to transmit over the Internet. Hard drives were physically shipped to processing centers where supercomputers spent months combining and analyzing the data. Multiple teams worked independently, using different algorithms and approaches, to ensure the results were robust. What they were searching for was the black hole's shadow, a dark region created by the event horizon and the photon sphere surrounding it. Light from the hot accretion disk would outline this shadow, creating a distinctive ring of light around the black hole's silhouette. The size and shape of this ring would confirm theoretical predictions and provide measurements of the black hole's mass and spin. The results were announced on April 10, 2019, in simultaneous press conferences around the world. The image showed exactly what theory predicted: a bright, asymmetric ring of light surrounding a dark central region. The first direct visual evidence of a black hole's event horizon. The bright ring was light from the accretion disk, bent and magnified by the black hole's intense gravity. The dark region was the shadow, slightly larger than the event horizon itself, representing the zone from which no light can escape to reach us. The image was blurry, limited by the resolution of the Earth-sized telescope, but it was undeniably a black hole. The size of the shadow matched predictions based on the black hole's mass estimated from stellar motions. The bright crescent on one side of the ring was consistent with Doppler boosting, where material moving toward us appears brighter due to relativistic effects. Every detail fit the theoretical models. Scientists were jubilant. Decades of theoretical work, dating back to Schwarzschild's 1916 solution, had predicted what a black hole should look like. Now, for the first time, we could see one. The image was compared to seeing the Earth from space for the first time, or detecting gravitational waves, a watershed moment that transformed black holes from mathematical abstractions into observable reality. The EHT team didn't stop there. They continued observing, improving their techniques, and adding more telescopes to the array. On May 12, 2022, they released the second black hole image, this time of Sagittarius A*, the supermassive black hole at the center of our own galaxy. It showed a similar bright ring around a dark shadow, confirming that Sagittarius A* is indeed a black hole and providing measurements of its properties. Imaging Sagittarius A* was actually more difficult than imaging M87*, despite it being much closer. The reason is variability. M87* is so massive that gas takes days or weeks to orbit close to the event horizon. During the EHT's observations, the appearance of M87* remained relatively stable. Sagittarius A*, being smaller, has gas that orbits in just minutes. The appearance of its accretion disk changes on timescales shorter than the observation period, like trying to photograph a fidgeting child. The team had to develop new analysis techniques to average out this variability and reconstruct a reliable image. Both images represent incredible technical achievements. They required international cooperation, cutting-edge technology, and sophisticated analysis algorithms. They validated general relativity in one of the most extreme environments possible and provided strong evidence that event horizons exist. They also opened a new era in black hole astronomy, where we can directly image and study these objects rather than inferring their properties indirectly. Future improvements to the EHT, including additional telescopes and observations at multiple wavelengths, will provide even sharper images and potentially allow astronomers to make movies of black holes, watching material spiral inward and observing how the accretion disk changes over time. Space-based radio telescopes could extend the baseline beyond Earth's diameter, improving resolution further and allowing observations of more distant black holes. These various methods, from X-ray binaries to stellar orbits to gravitational waves to direct imaging, each provide complementary information about black holes. Together, they've transformed our understanding. Black holes are no longer theoretical curiosities but confirmed astrophysical objects that we can observe, measure, and study in detail. We've gone from wondering whether they exist to counting them, measuring their spins, watching them merge, and even taking their pictures. Let's linger a moment longer on these historic images, because they represent not just technical achievements but profound philosophical milestones. For more than a century, black holes existed primarily on chalkboards and in equations. They were solutions to differential equations, thought experiments, theoretical predictions. Scientists believed in them, but belief based on indirect evidence is fundamentally different from directly seeing something with your own eyes, or in this case, your own telescopes. The image of M87*, released on April 10, 2019, changed everything. It shows a fuzzy orange ring, glowing brightly on one side, fading on the other, surrounding a dark central region. The ring is about 40 billion kilometers in diameter, several times the size of our solar system, though at 55 million light-years away, it appears incredibly tiny on the sky. The bright ring is light from the accretion disk, the superheated gas spiraling around the black hole at relativistic speeds. The asymmetry, where one side appears brighter, is due to relativistic beaming. The gas on the left side of the image is moving toward us at a significant fraction of the speed of light. Due to the Doppler effect and special relativistic effects, light from this approaching material is amplified, appearing brighter. The gas on the right side moves away from us, so its light is dimmed and redshifted. The dark region in the center, about 40 microarcseconds across, is the shadow. It's not the event horizon itself but rather the region encompassing the horizon and the photon sphere, from which no light can directly reach us. The size of this shadow provides a direct measurement of the black hole's mass. The EHT observations confirmed a mass of about 6.5 billion times the Sun, consistent with previous estimates from stellar and gas dynamics but now measured independently through the shadow size. The ring's shape is nearly circular, indicating that we're viewing the black hole from a relatively face-on angle, looking down on the accretion disk rather than edge-on. The slight asymmetry in brightness around the ring provided information about the disk's orientation and the direction of the black hole's spin. What's remarkable is how closely the image matches theoretical predictions. Scientists had simulated what black holes should look like for decades, using general relativistic ray tracing to follow light paths through the warped spacetime. The EHT image looks almost identical to these simulations. It's a stunning confirmation of Einstein's theory in an extreme environment where gravity is so strong that spacetime is bent into nearly unimaginable shapes. The public reaction was overwhelming. The image appeared on news sites, social media, and even inspired memes and artistic works. It captured imaginations in a way that few scientific discoveries do, perhaps because it made the invisible visible, giving concrete form to something previously abstract. For many people, the image made black holes real in a visceral, immediate way. Behind the image was an extraordinary effort. The EHT collaboration involved over 200 scientists from institutions around the globe. They had to coordinate observations across 8 telescopes, accounting for Earth's rotation, atmospheric conditions, and equipment limitations. They recorded 5 petabytes of data, equivalent to about 5,000 years of MP3 audio, stored on hundreds of hard drives. Processing this data required sophisticated algorithms. The raw data consisted of radio signals recorded at each telescope, precise measurements of amplitude and phase as a function of time. To create an image, these signals had to be correlated, comparing data from pairs of telescopes to extract information about the source's structure. But the EHT doesn't collect enough data to uniquely determine an image. There are many possible images consistent with the measurements. To solve this problem, multiple teams used different imaging algorithms, each making different assumptions about how images should be reconstructed. Some algorithms preferred smooth images, others allowed more structure. Some incorporated prior knowledge about black hole physics, others were more agnostic. The fact that all these independent approaches produced consistent results, all showing a bright ring around a dark shadow, gave confidence that the image was real and not an artifact of the analysis. One of the leading figures in developing these algorithms was Katie Bauman, whose work on imaging techniques for the EHT began during her graduate studies. When the M87* image was revealed, a photo of Bauman reacting to the first images went viral, highlighting her contributions and inspiring countless young scientists. The image of Sagittarius A*, released 3 years later on May 12, 2022, was in some ways even more impressive. Sagittarius A** is the black hole at the center of our own galaxy, about 27,000 light-years away. It's much smaller than M87**, with a mass of only about 4 million suns, so its shadow is also smaller, though fortunately, being closer, it appears about the same angular size on the sky. The challenge with Sagittarius A** was its variability. Gas near this black hole orbits in just minutes, so the appearance of the accretion disk changes faster than the EHT can observe it during a single night. It's like trying to take a clear photo of a child running around, they end up blurred. The EHT team had to develop new techniques, essentially taking thousands of snapshots and averaging them to produce a stable image. The resulting image shows a similar bright ring surrounding a dark shadow, confirming that Sagittarius A** is indeed a black hole. The ring is about 52 microarcseconds in diameter, consistent with theoretical predictions for a black hole of this mass. The image is slightly more symmetric than M87**, suggesting a different viewing angle or different properties of the accretion flow. Having images of two black holes, with very different masses in very different environments, allows for comparisons. Both show the predicted ring and shadow structure, strengthening confidence in general relativity. The similarities suggest that the fundamental physics governing black holes is the same regardless of mass, while the differences reveal how local conditions, like the rate of gas supply and the presence of magnetic fields, affect the accretion process. These images are just the beginning. The EHT continues to operate, with improvements planned. Additional telescopes are joining the array, increasing its sensitivity and resolution. Observations at multiple radio wavelengths will provide color information, revealing more about the temperature and density of gas in the accretion disk. Observing the same black holes repeatedly over months and years will allow astronomers to make movies, watching material spiral inward in real time. Future observations might detect the shadows of other black holes, both supermassive black holes in nearby galaxies and potentially even stellar mass black holes if they're in favorable configurations. Each new image will provide tests of general relativity and insights into the physics of accretion and jet formation. There's even talk of extending the baseline beyond Earth by placing radio telescopes in space. A satellite in Earth orbit could work in concert with ground-based telescopes, effectively creating a telescope larger than Earth and providing even sharper images. Such missions are still in the planning stages, but they represent the next frontier in black hole imaging. The images of M87* and Sagittarius A* are more than pretty pictures. They're scientific data, packed with information about spacetime, gravity, and astrophysics. They've confirmed theoretical predictions, measured black hole properties, and opened new avenues for research. They've brought black holes out of the realm of pure theory and into the realm of observational astronomy. And perhaps most importantly, they've captured the public imagination, inspiring wonder and curiosity about the universe's most extreme objects. In a very real sense, these images represent a kind of seeing that would have been incomprehensible to earlier generations. We've looked across millions of light-years of space, through clouds of gas and dust, past billions of stars, and resolved the shadow of an event horizon, the boundary beyond which nothing can return. We've photographed the edge of the unobservable. It's a testament to human ingenuity, curiosity, and the power of science to reveal hidden truths. Black holes are not isolated oddities. They're integral parts of the cosmic ecosystem, influencing the formation and evolution of galaxies, regulating star formation, and participating in some of the most energetic phenomena in the universe. To understand the cosmos, we must understand the role black holes play within it. Let's start at the heart of galaxies. Observations over the past few decades have revealed that essentially every large galaxy contains a supermassive black hole at its center. The relationship between galaxy and black hole is remarkably tight. The black hole's mass correlates strongly with properties of the galaxy's central bulge, the spherical concentration of stars at the galaxy's core. Specifically, the black hole mass is typically about 0.1 to 0.5% of the bulge mass. This correlation is surprising. The black hole, despite its enormous mass, is tiny compared to the galaxy. Sagittarius A*, for instance, has a mass of 4 million suns, but the Milky Way contains about 200 billion stars. The black hole is only 0.002% of the galaxy's stellar mass. And yet, there's a clear relationship between black hole mass and galaxy properties. This suggests that black holes and galaxies grow together, influencing each other despite the vast difference in scale. One mechanism for this coevolution is feedback. When a supermassive black hole feeds, the accretion disk and jets release enormous amounts of energy. This energy heats surrounding gas, preventing it from cooling and collapsing to form stars. In the most massive galaxies, this feedback may have shut down star formation billions of years ago, explaining why these galaxies are now full of old stars with little ongoing star formation. Observations support this picture. The most massive galaxies, called elliptical galaxies, are red, dominated by old stars, and contain little gas or dust. They also contain the most massive supermassive black holes. The energy released by these black holes, particularly through jets that can extend far beyond the galaxy itself, is sufficient to heat the surrounding intergalactic gas and prevent it from falling back into the galaxy to form new stars. In galaxy clusters, where many galaxies are bound together by gravity in a common halo of dark matter and hot gas, the effects of black hole feedback are even more dramatic. The central galaxy in a cluster often hosts an extremely massive black hole. Jets from this black hole inflate enormous bubbles in the surrounding hot gas, visible as cavities in X-ray images. These bubbles can be hundreds of thousands of light-years across, requiring enormous amounts of energy to create. The energy pumped into the cluster gas by the black hole prevents it from cooling and forming stars at the high rates that would otherwise occur. Without this feedback, the central galaxies of clusters would form stars at rates of hundreds or thousands of solar masses per year. Instead, they form stars at much lower rates, if at all. Black holes, despite being tiny, regulate the growth of galaxies millions of times more massive. This relationship between black holes and galaxies extends to the early universe. Astronomers have found supermassive black holes in galaxies that formed less than 1 billion years after the Big Bang. These black holes are already hundreds of millions or even billions of solar masses, implying they grew very rapidly in the early universe. Understanding how they formed and grew so quickly is one of the major challenges in modern astrophysics. One possibility is that the first generation of stars, massive and short-lived, left behind black holes that became the seeds for supermassive black holes. Another idea is that supermassive black holes formed directly from the collapse of massive gas clouds in the early universe, skipping the stellar stage entirely. Whatever the mechanism, the presence of massive black holes in the early universe suggests they played a crucial role in galaxy formation from the very beginning. Black holes are also associated with some of the most luminous objects in the universe, quasars and active galactic nuclei. A quasar is a galaxy with a supermassive black hole actively feeding at a high rate. The accretion disk around the black hole can outshine the entire galaxy, making quasars visible across billions of light-years. The most distant quasars we've observed are so far away that their light has traveled for over 13 billion years to reach us. We see them as they were when the universe was less than 1 billion years old. Quasars were much more common in the early universe than they are today. This tells us that supermassive black holes were feeding more actively in the past, when gas was more plentiful and galaxy mergers were more frequent. Today, most supermassive black holes are relatively quiet, including our own Sagittarius A*, accreting at much lower rates or not at all. Different types of active galactic nuclei, such as Seyfert galaxies, radio galaxies, and blazars, are thought to be the same basic phenomenon viewed from different angles. The unified model of AGN proposes that all AGN consist of a supermassive black hole surrounded by an accretion disk, with jets perpendicular to the disk. When we view the disk edge-on, we see one type of AGN. When we view it face-on, we see another. When a jet points directly at us, we see a blazar, one of the most luminous objects in the universe. Black holes also participate in cosmic collisions. When two galaxies merge, their central supermassive black holes eventually sink to the center of the merged galaxy and form a binary system. Over millions of years, they spiral together, emitting gravitational waves and losing orbital energy. Finally, they merge into a single, larger black hole. These supermassive black hole mergers are some of the most energetic events in the universe, releasing more energy in gravitational waves than all the stars in the observable universe emit as light during the same time. We haven't yet directly observed supermassive black hole mergers with gravitational waves because their frequencies are too low for current detectors like LIGO and Virgo. Ground-based detectors are sensitive to frequencies around 100 Hz, produced by stellar mass black hole mergers. Supermassive black hole mergers produce frequencies around 0.0001 Hz, requiring detectors with much longer arms. The planned space-based observatory LISA, with arms millions of kilometers long, will be able to detect these mergers when it launches in the 2030s. In the meantime, astronomers search for supermassive black hole binaries using other methods. Some galaxies show evidence of two active nuclei, suggesting two supermassive black holes that haven't yet merged. Radio observations reveal jets with periodic wobbles, possibly caused by a binary black hole system. Pulsar timing arrays, which monitor the precise timing of radio pulses from pulsars scattered throughout the galaxy, can detect the gravitational waves passing through our region of space from distant supermassive black hole mergers. Recent results from pulsar timing arrays suggest they may have detected the background hum of gravitational waves from many such mergers occurring throughout the universe. Black holes also affect their surroundings through more gentle means. The gravitational influence of a supermassive black hole can dynamically heat stars in the galaxy's central region, puffing up the stellar distribution and creating a low-density core. This is observed in many elliptical galaxies, where the central density of stars is lower than expected, carved out by the black hole's gravitational influence over billions of years. Occasionally, a star wanders too close to a supermassive black hole and is torn apart in a tidal disruption event. Half the star's material escapes, while the other half is accreted, producing a bright flare lasting months or years. These events are relatively rare in any given galaxy, occurring perhaps once every 10,000 to 100,000 years, but in the observable universe with its billions of galaxies, several are detected each year. Each provides a unique laboratory for studying black holes and stellar physics. Stellar mass black holes, though less influential than their supermassive cousins, also play roles in cosmic evolution. They're the endpoints of stellar evolution for the most massive stars, locking away a significant fraction of the heavy elements those stars produced. In dense stellar environments like globular clusters or the centers of galaxies, stellar mass black holes can undergo multiple mergers, building up to intermediate masses and potentially seeding supermassive black holes. Binary black hole systems, detected through gravitational waves, reveal the complex lives of massive stars. Some systems show black holes spinning in different directions or with unexpectedly high masses, suggesting formation scenarios involving dense stellar environments or exotic channels like repeated mergers. Looking to the far future, black holes will be among the last structures in the universe. Long after stars cease to form and galaxies evaporate, black holes will remain, slowly evaporating through Hawking radiation. The process will take unimaginably long, but eventually, even supermassive black holes will vanish, leaving behind only the faint glow of radiation dispersing into an increasingly cold and empty cosmos. But that's trillions upon trillions of years in the future. For now, black holes are active participants in the ongoing story of the universe, shaping galaxies, powering quasars, merging and growing, and providing us with endless opportunities to probe the fundamental laws of physics. They're not cosmic dead ends but rather dynamic engines of change, mystery, and discovery. We stand at an exciting moment in black hole astronomy. After decades of theoretical work and indirect observations, we've entered an era where black holes can be directly detected, imaged, and studied in unprecedented detail. But as much as we've learned, enormous mysteries remain, and the coming decades promise new discoveries that will further transform our understanding. One major frontier is improving gravitational wave detection. Current ground-based detectors like LIGO, Virgo, and CAGRA have opened the field, detecting dozens of black hole mergers. But they're sensitive only to stellar mass black holes, roughly 5 to 100 solar masses. Many interesting systems lie beyond their reach. The next generation of ground-based detectors, including upgrades to existing facilities and new observatories like the proposed Einstein Telescope in Europe and Cosmic Explorer in the United States, will be far more sensitive. They'll detect mergers at greater distances, probe the properties of black holes with higher precision, and observe systems throughout most of the visible universe. Space-based gravitational wave observatories will open an entirely new window. LISA, the Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will consist of 3 spacecraft in a triangular formation, separated by millions of kilometers. LISA will detect gravitational waves at frequencies far below what ground-based detectors can observe, making it sensitive to supermassive black hole mergers, the inspiral of stellar mass black holes into supermassive black holes, and potentially even signals from the early universe. Observing supermassive black hole mergers with LISA will allow us to study how galaxies and their black holes co-evolve. We'll be able to measure black hole spins and masses with exquisite precision, test general relativity in regimes never before accessible, and potentially detect unexpected sources that might reveal new physics. Another exciting prospect is the detection of intermediate mass black holes. These elusive objects, if they exist in large numbers, could be detected through their gravitational wave signals, through tidal disruption events if they lurk in galactic outskirts, or through careful searches of dense star clusters. Finding and characterizing intermediate mass black holes would help solve the mystery of how supermassive black holes form and grow. In imaging, the Event Horizon Telescope continues to improve. Adding more telescopes to the array, observing at multiple frequencies, and increasing the data collection rate will produce sharper images and enable movies of black holes. We'll be able to watch material spiral into the black hole in real time, observe flares and variability in the accretion disk, and potentially detect features like the photon ring, a series of nested bright rings produced by light that orbits the black hole multiple times before escaping. Future space-based radio telescopes could extend the baseline beyond Earth, providing even higher resolution. Such missions could image smaller black holes or observe more distant ones, expanding the catalog of imaged black holes from 2 to dozens or more. Theoretical work continues to probe the deep questions raised by black holes. The information paradox, while perhaps resolved in principle through insights from holography and quantum gravity, still lacks a complete, detailed solution. Understanding exactly how information escapes from an evaporating black hole, and what it means for the nature of spacetime, remains an active area of research. String theory, loop quantum gravity, and other approaches to quantum gravity all make predictions about what happens at the singularity. As these theories develop, they may provide testable predictions that can be compared with observations. The singularity itself might not be a true point of infinite density but rather a quantum structure, a Planck-scale region where space and time dissolve into something more fundamental. Black hole thermodynamics continues to reveal deep connections between gravity, quantum mechanics, and information theory. Some physicists believe that the holographic principle, which emerged from black hole physics, is a fundamental principle of nature, suggesting that the three-dimensional universe we experience might be encoded on a two-dimensional boundary, like a hologram. If true, this would profoundly change our understanding of reality. Another area of active research is black hole astrophysics. How do black holes form from the collapse of massive stars? What role do they play in galaxy evolution? How do jets launch, and what mechanisms govern their extraordinary power? How do binary black holes form, and what determines their properties? All these questions are being addressed through observations, simulations, and theoretical modeling. Multi-messenger astronomy, combining gravitational waves, electromagnetic observations, and potentially neutrinos, will provide comprehensive views of black hole systems. When LIGO detected a neutron-star merger in 2017, telescopes around the world observed the electromagnetic counterpart, from gamma rays to radio waves. A similar event involving black holes might reveal new phenomena, though black hole mergers are not expected to produce as much electromagnetic emission as neutron-star mergers. Advanced computer simulations play a crucial role in black hole research. Simulating the inspiral and merger of black holes requires solving Einstein's equations in their full complexity, a task only possible with supercomputers. These simulations provide the templates that allow gravitational wave detectors to identify signals and measure black hole properties. They also help interpret observations of accretion disks, jets, and tidal disruption events. Artificial intelligence and machine learning are becoming important tools. The algorithms used to reconstruct the EHT black hole images incorporated machine learning techniques. AI is being used to sift through gravitational wave data to find weak signals, to classify different types of active galactic nuclei, and to model complex astrophysical processes. As datasets grow larger and more complex, these tools will become increasingly essential. There's also the possibility of entirely unexpected discoveries. Black holes have surprised us before, and they'll likely do so again. Perhaps we'll find evidence of primordial black holes, or discover that black holes can form through mechanisms we haven't imagined. Perhaps gravitational wave observations will reveal deviations from general relativity, hints of new physics. Perhaps we'll detect exotic objects like wormholes or naked singularities, if they exist. The history of black hole research is a story of theoretical predictions confirmed by observation. Often decades later. From Michel's dark stars to Schwarzschild solution to Hawking radiation to gravitational waves to direct imaging, each theoretical prediction eventually found its observational counterpart. This gives confidence that the current theoretical predictions, like Hawking radiation from astrophysical black holes or the ringdown of merged black holes, will also eventually be confirmed. For students and young scientists, black hole research offers endless opportunities. The field is vibrant, interdisciplinary, and full of unsolved problems. It combines fundamental physics, astronomy, computational science, and engineering. It requires collaboration across institutions and countries. And it addresses some of the deepest questions humans have ever asked about the nature of reality. As we look forward, we can be confident that black holes will continue to be a central focus of physics and astronomy. They're not just fascinating objects in their own right but also tools for exploring gravity, quantum mechanics, and the structure of spacetime. Every new observation, every refined theory, every technological advance brings us closer to understanding these remarkable objects and, through them, the universe itself. Before we close our cosmic journey, it's worth reflecting on how black holes have captured not just the scientific imagination but the popular imagination as well. Few scientific concepts have so thoroughly permeated popular culture, inspiring everything from science fiction stories to philosophical musings to works of art. Part of the appeal is the name itself. Black hole is evocative, mysterious, and a little bit ominous. It conjures images of cosmic drains, portals to other worlds, or gateways to oblivion. The term was coined by physicist John Wheeler in 1967, though he didn't invent it so much as popularize it. Previously, these objects were called frozen stars or collapsed stars, terms that were technically accurate but lacked poetry. Wheeler understood that a good name can help a concept take hold, and black hole certainly did that. In science fiction, black holes have served as plot devices for decades. They're portrayed as shortcuts through space, as time machines, as energy sources, or as cosmic hazards. Some of these portrayals have basis in actual physics, while others are purely imaginative. The wormhole idea, where a black hole might connect to another region of space or time, comes from solutions to Einstein's equations, though whether such structures can exist in reality is highly doubtful. One of the most scientifically accurate portrayals of a black hole in popular media came in the 2014 film Interstellar. The movie's black hole, Gargantua, was rendered using calculations by physicist Kip Thorne and his team, who used general relativistic ray tracing to determine what the black hole and its accretion disk would actually look like. The resulting images showed the disk appearing to wrap above and below the black hole due to gravitational lensing, and one side appearing brighter due to Doppler effects. These visualizations were so detailed that they led to scientific papers published in academic journals. Black holes also appear in discussions of philosophy and metaphysics. They're used as metaphors for death, for the unknown, for fears and anxieties that seem to swallow everything. The event horizon becomes a point of no return, a boundary we cannot cross and return to tell the tale. The singularity represents the limits of knowledge, the place where our understanding breaks down. There's something deeply human about our fascination with black holes. They represent the ultimate extreme, the most powerful gravitational pull, the darkest darkness, the point where space and time themselves break down. They challenge our intuitions and push the boundaries of what we can comprehend. In a universe that often seems designed for human habitation, black holes are decidedly inhuman. Places where the normal rules simply don't apply. At the same time, studying black holes reveals the power of human reason. We predicted their existence through pure mathematics, we detected them through ingenious observations, and we imaged them through international collaboration and technological innovation. Black holes might be alien and extreme, but our ability to understand them demonstrates that the universe, however strange, is not beyond our grasp. Black holes also raise questions about destiny and inevitability. Once something crosses the event horizon, its fate is sealed. No escape is possible. This mirrors our own relationship with time. We move inexorably forward into the future, unable to return to the past. In this sense, We all live beyond our own personal event horizons, our past sealed off from influence, our futures uncertain but inevitable. The scientific study of black holes has philosophical implications as well. The information paradox raises questions about the nature of information and whether physical laws truly preserve it. The holographic principle suggests that reality might be simpler than it appears, with the three-dimensional world we experience emerging from information encoded on a two-dimensional surface. These ideas challenge our basic notions of what it means for something to exist. For many people, black holes represent the romance of science, the quest to understand nature's mysteries through observation and reason. They embody the excitement of discovery, the satisfaction of seeing predictions confirmed, and the humility of confronting phenomena far beyond everyday experience. They remind us that we live in a universe far stranger and more wonderful than our ancestors imagined. In education, black holes serve as gateways to physics. Students who might find physics abstract or boring often become engaged when learning about black holes. They're intrinsically interesting, combining elements of mystery, danger, and scientific detective work. Teaching about black holes naturally leads to discussions of gravity, relativity, quantum mechanics, and astrophysics, covering much of modern physics through the lens of a single fascinating object. Artists have also been inspired by black holes. Paintings, sculptures, music compositions, and poems have all taken black holes as subject matter. The first image of M87* quickly became iconic, appearing in art installations and inspiring creative works. The blend of scientific imagery and abstract beauty resonates with artists who see in black holes reflections of human creativity and the sublime. Black holes even influence how we think about the future. In scenarios for the far distant future of the universe, black holes play a central role. Long after stars have burned out and galaxies dispersed, black holes will remain, slowly evaporating into the void. The final era of the universe, trillions of years hence, is sometimes called the black hole era, when these objects dominate the cosmos before they too fade away. There's something melancholy but also beautiful about this vision. The universe begins in a blaze of light, the Big Bang, and ends in quiet darkness, with the last black holes evaporating in nearly absolute cold and emptiness. It's a cosmic narrative with a clear arc, from beginning to end, and black holes mark the final chapters. But perhaps we shouldn't think of black holes as endings. They're also beginnings, the birthplaces of new physics, the frontiers where our understanding is tested and expanded. Every question they raise leads to new insights. Every mystery they present invites new theories. They're not cosmic tombstones but rather laboratories, classrooms, and inspiration. As we lay here, thinking about black holes, perhaps drifting towards sleep, we can appreciate them not just as astrophysical objects but as symbols of human curiosity and achievement. From a country rector wondering about dark stars to scientists capturing images of event horizons, the story of black holes is a story of imagination, persistence, and the desire to understand our place in the cosmos.